Hey guys, so this is part 3 and we'll continue talking about the screws. If you have an long oblique fracture or a spiral fracture and you would like to fixate this fracture with only screws, no plates, you could place 3 screws through this fracture. An example of this is an oblique fracture of one of the metatarsal bones or also the distal fibula. So which screw will you place first? The most central screw, the most distal, or the most proximal screw? So the answer for this is very simple. The central screw is the one that is most likely to be perpendicular to both bone and fracture site. So you will start with that screw, and because you will prevent telescoping if you place that screw, and also you will prevent any mismatch between the two fragments of the fracture site if you start with that screw. So you can start with the central screw and then you can place either the proximal or the distal screws. Now, what is the difference between cortical and cancellous bone? So a misconception is that within the center of the bone, that's where you have the cancellous bone and the cortical bone is on the sides. That's not true. The truth is towards the end of the bone, both epiphyses, you have a lot of cancellous bone. And in the shaft of the bone, that's where you have the cortical bone. As you can see here, this is all cortical bone. It gets thinner and thinner and thinner as you go distally. And cancellous bone is the predominant bone towards the end of each bone. So if you are going to use a cancel screw, the correct placement is towards the end of the bone, while any shaft fracture should be fixated with cortical screws. It's also very important to note that cancellous screws supposed to be within the cancellous bone. Look how the tip of that screw is buried within the bone, while cortical screws need to extend beyond the bone surface to make sure that they are engaging the far cortex as well. If the cancellous screw is measured 15, then you ask your scrub tech to give you a 14 length screw because you do not want the screw to back off the cortical bone because that screw will have hard time penetrating the far cortex because there is a little bit of cortical bone here and that screw is cancellous. While for cortical bone, if you measure 15, you ask for 16 or larger because you want to make sure that the cortical screw has penetrated and engaged the far cortex as well. It's important to note that cortical bone is hard, and that's why deep threads are not needed to ensure the hold of the screw. Cortical screws are therefore designed with shallow threads. The threads of the cortical screws have fine pitch and they are closer together. This design minimizes the insertion force that is needed to be applied by the surgeon. The screw does not advance very far in the bone, in the hard bone, with each turn of the screwdriver, and the insertion force is then kept at a reasonable level, as we know that the pitch for the cortical screws is much less than the cancellous screws. The cancellous screws, on the other hand, does engage spongy or trabecular bone and that is being purchased at the metaphyses and epiphyses. That's why we have deeper threads and coarse pitch. This design maximizes the surface area of the threads that is in contact with the bone, thereby increasing the screw holding power in the soft bone. Because cancellous bone is soft, coarse, or large, pitches of the cancellous screws require only minimal force for insertion. So again, I have here smaller pitch, with each turn you're advancing only 1.25 millimeter. Here I have a larger pitch, so with each turn I'm advancing 1.75 millimeter. This way it's easy to do this in spongy bone versus hard bone. At the same time, the threads here are small because I do not need a large surface area because the bone is thick. The threads here are much deeper because I want to engage a bigger surface area of the bone for a better purchase. So here's an example again. That will be an example of a cancellous screw, has deeper threads and bigger pitch and smaller core diameter for the same size screw versus a cortical screw that has a smaller pitch and shallower threads and has a larger core for the same size screw. When we advance these, as you could see, the cancel screw travels a longer distance than the cortical screw. Now we'll talk about the lag by technique and design and other modalities as well. So first, lag by AO technique, we have over drill, then under drill, etc. This is the standard technique. If you go with under drill first, then over drill, that will be the alternative technique. Both of these are correct and both of these are called lag by AO technique. So if this is my over drill, which is the same size of the screw diameter, I penetrate the near cortex and then I can put my sleeve here. The sleeve will rest, as you can see, on the far cortex, and at this point I can use my under drill to penetrate the far cortex. Next point is my countersink, which is very easy to do over the over drill hole in case of a perpendicular insertion of the screw. So you do it here and then you measure, and after you measure you start doing your tapping. You do not tap before you measure. I know that there are most of the screws now are self-tapping, but the AO technique includes tapping, and the Podiatry Institute actually likes to perform tapping. So if you tap, you do this after you measure, not before you measure. The reason for that is the following. Measuring device will destroy your thread if you tap first. So you need first to measure and then you make the threads within the bone. Otherwise, this long metal will actually destroy your threads that you have already formed by tapping. So you tap after you measure. Then you insert your screw, and as you can see, you'll get compression. So as the screw travels through the far cortex, it will start engaging the far cortex but will not engage the near cortex. In the near cortex, the screw is just spinning. In the far cortex, the screw is catching or engaging the cortex or purchasing the cortex, and that's how you get compression. Another important point, as you can see, we first countersink before we measure, and the reason for that is that you want to get a correct measurement of the screw length. You want to measure after you have already countersunk and you remove the excess bone that is for the head of the screw. Now, if you do not drill the gliding hole, what's going to happen? What's going to happen if you do not over drill? Well, if you not over drill, the screw is going to engage both the near cortex and the far cortex. And as the screw come through the far cortex, you will actually increase the distance at the fracture site. So you will distract your fracture even more. Next is the lag by design, which basically means that the screw is designed to perform the lag technique itself. So the screw is partially threaded. So lag by design basically means partially threaded screw, and you do not need to over drill in this case because there are no threads on the proximal portion of the screw. Hence, there are no threads to engage the near cortex, so you only under drill. And as you can see, the diameter of the screw is bigger in the threaded portion versus the non-threaded portion of the screw. The only problem with this is that you need to make sure that the threads travel past your fracture site. Otherwise, you will not be able to bring the bones together. You will have more distraction if the threads do not cross the fracture site completely. Then another technique is called compromise compression technique. So in this technique, what you do is you bring the two bones together with a bone climb. You do not over drill, you just under drill, and you do the same steps like you normally would do with in a lag technique. What's the advantage of this technique? Well, the biggest advantage of this technique that the screw now is purchasing both near and far cortices. So you use a fully threaded screw, you bring the bones together with a bone clamp, strong bone clamp, and then you do make the under drill. There's no over drill, and the threads will engage both cortices and gives you a stronger design. Plate compression techniques. If using a plate, because you cannot use the screw across that fracture site, the fracture site is vertical to the bone. There is no way that you can place lag screw here. So what do you do? So you can place a compression plate. You can insert your screws and then try to bring the bone together. How do you do this? Well, first let's see what's wrong to do. If you drill through the center of the hole, you will not be able to do any compression. So you can utilize dynamic compression plate in order for you to compress the fracture site utilizing a plate. The screw holes in a dynamic compression plate are best described as a portion of an inclined or angled cylinder. So like a ball, the screw head slides down the inclined shoulder of the cylinder. So what happens is the screw is inserted. As a screw is inserted and tightened, this results in movement of the bone fragments relative to the plate and consequently doing a compression across the fracture. You can obtain up to 1 millimeter of compression this way. So let's see how this happens. You insert your screw, the screw travels this way here. Look what happened here. So I drill this way, away from my fracture. I drill also here, away from my fracture. And as I insert my screw, what happened is the screw is trying to get to the hole. So it will move the plate away from the fracture. As you're doing this, you're getting compression across the fracture site. There's also another point to consider while you're doing the plate compression technique, which is you have to bend the plate away from the bone, because what's going to happen if you do not bend the plate, you put the plate flat on the bone, you're drilling away from the fracture site. As the compression is happening here, you will get compression to the side of the plate, and you will get distraction away from the plate. And the reason for that is that the screw head will move more than the distal end of the screw. So in order for you to avoid this and get an equal compression on both sides, you bend the plate as you see here. You insert your screws this way. You tighten the screws simultaneously or one after the other, and this way you get a uniform compression across the fracture site. And this is a good example of fractures that happen in the metatarsal bones. It's very important to know that, especially in the metatarsal bones, the distraction site is plantar, or the tension site is plantar, while the compression side of the fracture is always dorsal. So you really have to bend the plates that way. If you bend them the opposite way, you will get distraction plantarly. Now we'll go to part number 4. Thank you.